Okay, so so we're going to prove the Picard-Lindelöf theorem, and we'll see, it may take us, we may need to continue on it also on Tuesday, and then when we're done with it, we will just do review on Tuesday, but let's see how far we get. So the Picard-Lindelöf theorem is the following theorem, and it said that it's a ODE, so it's what's called the ordinary differential equation. And so again, a differential equation is something about an unknown function and its derivative, right? So a differential equation just means it's an equation. So this here means that it's an equation in an unknown function and its derivative. Ordinary, just as we talked about last time, ordinary refer to that is just of one variable, okay? And so the ODE that the Picard-Lindelöf theorem is about is, so the unknown function is y, and the ODE is this, that we want the derivative of this unknown function to be equal to a function of the unknown function plus another function that just depends on x. So y here is the unknown function, and y is a function of x. Right? X is a real number, right? And it's just yeah. So this is the differential equation, and then we have some initial condition. So at 0, we want it to take a value a. Okay. So this is the differential equation, and what we assume here is, so f and g are function on R, and you should think about those as being known, and they are, and f here is differentiable, and the derivative is continuous, and g is just continuous. Doesn't need to be differentiable. And the Picard-Lindelöf theorem is, so again, the Picard-Lindelöf theorem is the following, that given f g as above, and sorry, and a was this constant, it's just a real number, as above, there exist delta greater than 0, such that, and a solution y defined on the interval from minus delta to delta, and solution y to the ODE, right? And so again, meaning that is solution, that means that at 0 it takes value a, and then it's satisfying that equation. Okay. And moreover, and I'll get back to that, but we won't it's quite possible. I won't get to that today. Moreover, solutions are unique. Okay, and so this is like a standard problem. When you're looking at differential equations, you have a differential equation that may describe something in nature, and you wonder, does this equation have a solution? And if it has a solution, are solutions unique? Okay, so this is what this answer in this case. And the interesting thing, or part of the interesting thing, so this is a fundamental question used all over science and engineering. And one of the interesting things is that the proof of this uses metric spaces. And so the proof has been used, various versions of the proof have been used to prove existence and uniqueness of various differential equations. So the proof uses the theory of metric spaces, which is sort of surprising because it seems to have nothing to do with metric spaces. And so it uses, in particular, the metric space that it's using is the continuous functions on some interval here. Right, and on the space of continuous function, we have the metric that we talked about. The metric, so if f and g, sorry, f is so bad because it's the and g also. Let's call it h1 and h2. Suppose that these are continuous functions, h1 and h2 are continuous functions on an interval like this. Then the distance is this that we have considered various times. This is just the maximum over x in this interval here of f of x, of h1, h1 of x minus h2 of x, and then the absolute value of that. Right. So this is the distance on the space of continuous functions that we have looked at a lot. Okay, and it's actually not quite this space, as I mentioned last time. It's a ball in this space that is using. Right, okay. So what do we need about this metric space? So one thing we've proven a couple of lectures ago is that this space here of continuous functions with this metric here is Cauchy complete. So we're going to use that. Okay. Another thing we're going to use is this notion of contracting map. So another tool will be that of a contracting map. And so, and remember, this is a number of lectures ago. We talked about a contracting map, but we need a more general notion of contracting map, because when we talked about it, we talked about a map from R into R. And then we used this notion of contracting map to finding zeros with using Newton's method. Okay, but here we're going to use it for something different, and so we need a more general notion. So suppose that contracting map. So this is the general version, as opposed to the version that we talked about already, that was for for the line for R. So contracting map, sorry. And so this is, so you have a metric space XD. This is, it could be like this, but it also just could be any metric space. And then you have a map from this metric space into the self. And T here is said to be contracting. If there exists a constant C less than 1, such that if you're looking at the distance between the images, then they are squeezed together. So this distance here between the images under the map is less or equal to this constant that is less than 1 times the distance before you apply the map. Right, so this means that under the map, things get closer together, right? So that's a contracting map. And so now we proved a theorem when we did the Newton method. We proved a theorem, but we needed about fixed points. And we need a generalized version of that. So if you take a map just in general from a space to a space, then a fixed point is a point x in the space, so that T of x, so T leaves x invariant, so T of x is equal to x. That's a fixed point, right? Okay, and so now if you have a contracting map, so if T here is contracting, then T can have at most one fixed point. Why? Because suppose that x, so if x and y are both fixed point, well, then you have that T of x is equal to T of y. Sorry, T of x is equal to x, and T of y is equal to y, right? And so now you have that the distance between T of x, let me make it a little more space. Then you have that actually we just continue down here. So that the distance between T of x, comma T of y, the map is contracting, so this is less or equal to this constant times this here. On the other hand, they're both fixed points, so T of x is x, this here is x, and this here is y. So if we write this out, so this is x comma y, and so you see that this thing here is some constant less than 1, strictly less than 1, times itself. So this means, of course, that this number here, this non-negative number, must be 0. And so this, of course, implies, by the actions of a metric space, that x is equal to y. Right? So a contracting map has at most one fixed point. Now, the other thing is that if you take a metric space, right, so this here is Cauchy complete. So now I'm going to take a Cauchy complete metric space. So it could be continuous function on some closed interval, and that's how we will apply it, but it works more generally. So we have the following theorem. So if this here is a complete, Cauchy-complete metric space, and T from X into X is a contracting map, then T has a unique fixed point. We know it only have at most one, so the statement really is that it has one, right? So it has a unique fixed point. Okay, so let's try to prove this. And you might remember, and if you don't, that's fine, but you might remember how we used it in the Newton methods. Because the Newton methods was like, it was a version of this on R. So you had a map from R to R, and to find the fixed point, and so you wondered what you were there in the Newton methods was something about finding a point where a function vanishes, right? And that was set up as a fixed point theorem. And so what you did is you made a good choice. I mean, a choice that looked reasonable, right? This is not exactly where the function vanishes, but something that looks close to where it vanished. And then you took the image under the map and you iterated this. And so it's the same we're going to do here. So, and this time we don't even need to make a good choice. So we just take, let X here be any point in the metric space. So you're just fixing some point in the metric space. And now you're looking at the sequence X, T of X, and then you apply T to T of X. So this is, I write this as this. And then you apply T to T squared of X. So that's T, right, like this. And so you keep applying T more and more times, right? And so this gives you a sequence, and so on. So this gives you a sequence, okay? And now the claim is that this sequence here, so claim that this sequence here converge to, right, so it converge, and the limit here, this here, is a fixed point. For T. So that's a claim, okay? Now, so we wanted to prove first that it's converging. Okay, so we're going to prove first. So we'll first show that Tn is a Cauchy sequence. Okay, so now let's look at, so we're supposed to look, if you're looking at if you try to prove that something is a Cauchy sequence, then you're looking at the distance between elements in the sequence where both of these elements is sufficiently far out, right? That's what you're supposed to look at. And so let me write the M here. So I can think about one of them as being further out than the other one. So I'm going to think about M here as being N plus some number K, right? Some integer K, right? And so I'm interested in estimating the distance between Tn of X and Tn plus K of X. Okay. Now, in order to do this, let me start with something simpler first. Let me look at the distance between t of x. Let me look at the distance between t L of x and t L plus 1 of x. Okay, so two consecutive elements in the sequence. Okay, now I can sing it. So this thing here, well, this is equal to the distance between t of t L minus 1 of x and then t of t L of x, like that, right? I can write it like that, right? But now, of course, so you see here, there's some element in x, so in the space x. Here's another element. They both have t applied to it. T is contracting, so you get c t L minus 1 x TL of x. So you see that if you take two consecutive elements and you're taking the distance, then it's bounded by this constant c times, right, where you have one less, where you have applied t one less time on both, right? These are again consecutive elements, but the highest one is one less, right? Okay, so now if you iterate this, okay, so iterating this, so let's see, maybe, okay, maybe let me wait with iterating. Let me just look at what we need. So we have this in here, and this here I can write as so here you see, here I can write this as t, the distance t, and then t n minus 1 x, and then t n minus 1 plus k x, like this, right? And so here I can use the same trick, that it gets c, and then d t n minus 1 x, comma t n minus 1 plus k of x, right? And this one here, I can keep going like this, right? I can keep going until there is I've used up all my n's, right? And so I can keep going, and so this is less or equal to c to the n. And then the last one I get is I get x, and then I get tk of x, right? I want to show that this thing here becomes small as long as n, remember k is a positive integer, as long as n is sufficiently large, right? So I need, this is a hopeful sign, because when n get large, this here get really, really small, right? But I still need to estimate this here, right? Now, so how do I estimate it? I'm using what I did over here. So so you're looking at, so you have the distance between x and tk of x. This thing here, I can use this triangle inequality. So I can say that this is less than dx t of x plus dt of x t squared of x plus dt squared of x like cube of x, and then all the way up to d t k minus 1 of x t k of x. Right, so this is just the triangle inequality, right? Now, this may seem rather bad estimate, but let's see how bad it is. So, right, so now this first thing here, I'm just leaving it. I can't do anything about that. So I need to just take that. This one here, so I'm using this with between two consecutive. So in this case, it's just bounded by c times d x tx, right? And the next one here, this one here is bounded by c squared d x tx. And the next, right, and so on, up to this one here is bounded by c k minus 1 d x t x, right? And so you see that now this here factor out. So this here is, so this factor out. And then in this bracket you get 1 plus c squared plus all the way up to c k minus 1. But this is a geometric series, right? This is a geometric series. And this is certainly less than when I take, remember c is strictly less than 1. So it's a geometric series, it's a convergent geometric series. So this here is less than d x t of x. And then this sum, well, it's less than when you're summing it all the way to infinity. So this is less than 1. This is the sum of the geometric series. C is strictly less than 1. Right, C is positive and is strictly less than 1. Okay. So you see now that we have, right, so we have that. So what we were interested in is, we were interested in saying that as long as I choose little n sufficiently large, then this thing here must be very small, right? And we know already that it's bounded like this, and now I fill in this, and you see this here, so this means that this is less than Cn, and then what you get here is 1 minus c, and then times d x t of x, right? X is fixed, and so you see that when little n is sufficiently large, then this whole thing here is as small as you want, right? So this means that what we have proven here is that this sequence here is a Cauchy sequence. So we've proven that, okay? Now, of course, this is where the assumption comes in, that this metric space is Cauchy complete, right? So since X, this metric space is Cauchy complete, and this sequence here is a Cauchy sequence, it is convergent, right? Yep.
Sorry, just back to that ended up quickly.
Yep.
Are you able to explain again how we got that? How we were trying, did we find a bound for the dx, tx, or we're just saying that?
Right, so I'm saying that x is fixed. You pick any point you want, and I claim that if I, it may be a very bad candidate for the fixed point, but it doesn't matter. It's okay. It may just take you longer to get to the fixed point, but you fix x, and then you're looking at this sequence. And then I claim that this sequence will be a Cauchy sequence, right? And so x is fixed, and so we have this inequality here. And what we need is that when little n is sufficiently far, large, then for all k is positive integer, right? This here is like further out than n. Then for all k, and this should be independent on k, this thing here is small. But this is just...
To get rid of the whole thing from the previous step was now it's not a tk of x, right? So...
Yeah, so since x is fixed, tx is fixed. So this is just a constant. Yeah. Okay. So right. So what we have proven is that we have this Cauchy complete metric space, and we have this sequence. X was fixed again. That is a Cauchy sequence. And so since this metric space is Cauchy complete, this is convergent, and I can denote the limits. So I just call the limit x infinity. Right, so if we have this. Now I want to show that so the next claim is that x infinity is a fixed point for t. Okay. So if I'm looking at the sequence here, suppose I take the sequence and suppose I take t of the sequence.